So, in the last lecture I have discussed about the Meyerhof bearing capacity theory and the Hansen bearing capacity theory. Now, this lecture I will discuss two more bearing capacity theories, which is proposed by the BASIC and the IS code or Indian Standard Code. So, in the BASIC also proposed the similar type of bearing capacity theory. So, that is, this is similar to the Hansen's equation. So, the NC NQ is same as Meyerhof recommendation, which is also similar to the Hansen's equation, but N gamma expression is different as compared to the Meyerhof theory and the Hansen's theory. And then that is why the table which is given only for the N gamma, because the NC and NQ value we can get from the Meyerhof table. So, and these are the, and then this bearing capacity equation is similar, only the N gamma value is big. So, we have to use the Hansen's corrections factors, depth factor, shape factor and inclination factor that we are using for the Hansen's table. But the only difference of the Hansen's and the basic bearing capacity theory is that N gamma value. So, that is why the this table is given for the N gamma. And then the next one is the IS code method. So, IS code, Indian Standard Code, also recommend the net ultimate bearing capacity. So, all the previous theories are given the ultimate bearing capacity, but IS code is given directly the net ultimate bearing capacity. That is why this NQ minus 1, because this minus 1 value means basically the minus gamma into df. So, in that form. So, that is why this minus 1 term is introduced. So, these are the NC, NQ, N gamma are the same, those are given by the basic. So, that means the NC, NQ are the Meyerhof's NC, NQ, and the N gamma is the basic N gamma. So, and then there is a water table effect is also incorporated. So, W dash is the factor for the water table. Here the SC, DC, IC is a shape factor, depth factor, inclination factor. Along that the water table factor is also incorporated. So, here the W dash value is 1 when the water is below the df by b. So, that means here, so which is the similar to the other cases. So, that means if we this is the ground surface and this is the df, depth of foundation, and this is the b, width of foundation, and if the depth of water table is here. So, that means the total depth is df by b, then definitely there will be no effect. So, and then that value is 1. Now, if this value is 0.5 when your W value is here. So, that means here W value is as the 1 when water table is at df or above that. So, that means from the below. So, that means if your df value within if your water table is within the df above the base of the footing, then the W dash value is 0.5. So, here the W dash value is 1 and here within this zone, total zone. So, W dash value is 0.5. So, this is the recommendation is given, and if, so that means here also 0.5. So, this point also 0.5 and here also 1. So, now if water table is in between the base of the foundation and within the B from the base, then we have to calculate the W dash in by linear interpolation. That means, here is 1, here is 0.5. So, if it is at B by 2 from the base, then it will be 0.75 like this. So, linearly we have to, so this will be 0.75 if it is at the base of the foundation. So, like this we have to linearly interpolate the values of the W dash, and here, and as it is mentioned that Q is the effective pressure which is acting on the base. So, and which is true for all the theories. So, next one So, these are the factors which is recommended for the IS code. This is the SC, SQ, S gamma. So, for rectangular, footy, square and circular, and these are the factors that we can use. And then this is for the depth factors, and for this is for any phi, and this is what greater than 10 and less than 10, and these factors we have to use, and this is for the inclination factors. So, these are the fact table for the IS code recommendation. And then till now we have discussed about the bearing capacity, how we can determine by the theories proposed by various researchers. Now, the bearing capacity of the granular soil can also be determined by the SPT test data. So, this is the proposed by the Teng 1962, where the net ultimate bearing capacity value we can determine for the strip footing and we can determine for the square and circular footing. So, these are the two equations. So, these equations or these recommendations are based on the observation. So, these are called the empirical relationship. So, these empirical relationships are given. So, these are coming from the observation, where this is the Q n, Q is the net ultimate bearing capacity, which is in kilonewton per meter square. N is the average N value corrected for overburden pressure. So, this is corrected only for the overburden pressure, not any other corrections is applied along the measure N value. So, that corrected N value corrected by overburden pressure is this N, and df is the depth of the footing, and if df is greater than b, then take df is equal to b. So, this is the recommendation, and so that means here what we have to do, that we have to know the R w dash and R w. So, these are the factors which is for the water table factors. So, that means how I can calculate R w dash and R w, because other things N value we can get, we will get the df value. If df is greater than b, we will get the df is equal to b, and then we will get the b is the width of the foundation. So, now and in case of circular, instead of b, it will be the radius r. So, that is obvious for all the equations. And then, but these two corrections for the water table. So, these are the chart we can use for this is. So, that means what is dw? There is a term dw and dw dash, rw and rw dash. So, dw is the depth of water table below the ground surface limited to the depth of equal to df. So, that means here if this is the ground surface and this is the foundation. So, this is the base of the foundation, this is the ground surface. So, this is df. So, dw is the if the water table at anywhere in between the ground surface and the base of the footing. So, this is the dw, and dw dash the depth of water table measured from the base level of the footing with a limited value equal to the width of the footing. So, that means here the similar to the influence zone, that will be the b. So, here if the water table is here, where this value is dw dash. So, these are the two. dw is water table is within the ground surface and base of the footing, and dw dash if the water table within the base of the footing to a depth up to width of the footing. So, these are the two values, and then we df and we divide it by df and the b, and then we got this chart, and from there if it is corresponding to dw by df, then it will be rw, and if it is corresponding to dw dash by b, then it will be rw dash. So, these two value will get, and we will put these two value in this equation, and we will get the net ultimate bearing capacity with the help of SPT value. And remember that again that this equation is given for the granular soil, because in all the field test, as I mentioned, is most suitable for the granular soil, and but for the cohesive soil, because we can collect the undisturbed soil sample. So, we can collect the undisturbed sample, take it to the lab, then test it, get the proper shear strength or bearing capacity equation parameters, and then we can get those parameters easily. So, that means, here these test it is suitable for these expression with the help of SPT is suitable for the granular soil. Then the next is that if it is the layered soil, then now we have discussed if the soil is the homogeneous. Okay. Now, if what will happen if we have the layered soil. So, now that means when you are talking about a layered soil, that means this is the foundation, and say below there is the one layer, this is the second layer, and this is the third layer, and these all are within the influence zone of the. So, this is within the B, because B is the influence zone for bearing capacity calculation. So, in that case what we are doing? We are doing that take the weighted average of the cohesion, because this is the C1 and this one say H1, this is C2, this is the H2. H2 is the thickness of the layer, and this C1 is the cohesion of the first layer, C2 is the cohesion of the second layer, and phi 1 is the cohesion of the first layer, phi 2 is the cohesion of the second layer, phi 3 is the cohesion of the third layer. So, all these this is phi 2 is the friction of the third layer. So, phi 1, phi 2, phi 3 is the friction of respective layers, and C1, C2, C3 is the cohesion of the respective layers. And if all these things is within the influence zone, then you have to take the weighted average of the C, and then again the weighted average of the phi by using these expressions. Okay. So, that is the one way we take care the if the soil is in layered soil. So, that way we can take care this thing. Another one, this theory is also developed for the layered soil, but for the design purpose in this course I will use this technique when this is the layered soil, and we will use in this way we will determine the friction and cohesion value by taking the weighted average. Now, this is very important, that what are the factor influencing the bearing capacity. Now, for C, if the first case, if your Cu undrained cohesion is equal to 0, that means if your it is a friction soil. So, if the undrained cohesion is equal to 0, so the first part will vanish, the C and C part will vanish. So, there will be only Q N Q plus half gamma B n gamma. So, that means your this n q n gamma is the function of phi. So, it is the function of relative density that is influencing the bearing capacity, or other way phi value. Then B is there. So, width of the footing is also influencing. Then depth of the footing, because your Q value is dF into gamma. So, depth of the footing is also influencing. Then unit weight of the soil is also influencing, because we have gamma value, and the position of the groundwater table, because as the position of the groundwater table changes, then you have to have your bearing capacity value will change. So, if it is the phi soil or the C equal to 0 case, or if it is the granular soil, then these 5 are the influencing factor for the bearing capacity. Now, if it is a C soil or cohesive soil, or phi is equal to 0, so then the ultimate bearing capacity will be Cu N C and plus N Q, because Cu undrained, because your phi is equal to 0, and Q. So, what are the factors is influencing? Because there is no B value. So, width of the footing does not have any influence on the bearing capacity if it is on purely clay soil. So, remember that width of the footing does not have any influence if you are determining the bearing capacity of a foundation which is resting on a purely cohesive soil. Now, if other term, this N C value, there also the phi factor is there, but here phi value is 0. So, N C value is also your 5.7 or 5.14. So, that is why phi is not influencing. So, your B is not influencing. So, and now if it is the ultimate, then definitely dF has the influence and the unit weight also has the influence. But if we are talking about net ultimate, so net ultimate will be, your net ultimate will be CUNC plus Q minus Q. So, this will be CUNC. So, if it is a net ultimate, then unit weight also does not have any influence. Cohesion or depth of the foundation also does not have any influence in the bearing capacity. It is only cohesion and then 5.7 or 5.14 depending upon your roughness of the footing. So, that means it is only the cohesion dependent value for if it is the net ultimate. And so, and when we are talking about, because there is water table also, when I discuss about the water table correction, then we have not applied any correction in first term, that is CNC term. So, water table also does not have any influence, but water table indirectly has an influence, but in that case this Cu value will be influenced by the water. So, as I mentioned, if there is a water, then in case of cohesive soil, you have to determine the Cu value under saturated condition. Till now we have discussed so many theories. Now, this is the first example that we are solving, that we are taking a common example and then we will determine the bearing capacity value by using all the available theories. Okay. So, the example that we are taking, the rectangular footing of size 3 meter cross 6 meter is founded at a depth of 1 meter in a homogeneous sandy soil. So, the water table is at a great depth, the unit weight of soil is 18 kilonewton per meter. So, this will be the meter cube. So, this will be the meter cube, 18 kilonewton per meter cube. Determine the net ultimate bearing capacity if C is equal to 0 and phi is equal to 40 degree. So, because it is a sandy soil, C cohesion value is 0 and the friction value is 40 degree, and this is a 3 cross 6 meter foundation and it is a homogeneous. And so, and in case of layer we will do the weighted average. So, but it is a homogeneous, and water table is a great depth. That means, water table is far below the a depth from the base of the footing. That means, you know, the if water table from the base of the footing is greater than the width of the footing, then we do not consider the water table effect. So, that means, water does not have any effect. So, that is why the unit weight of the soil, and the unit weight we are taking the uniform because it is a homogeneous soil. So, the first theory, if I use the Tarzaki's bearing capacity theory, so the net ultimate will be ultimate minus gamma dF, and dF is also 1 meter, depth of the foundation is 1 meter, and this is the equation, and we are taking NQ minus 1 because the gamma dF it is common for Q term. So, we are taking this equation. So, now from the Tarzaki's table, NQ value is 81.3 and N gamma value is 100.4 for corresponding to phi equal to 40 degree, and B is equal to 3 meter, L equal to 6 meter. So, net ultimate bearing capacity will be 3885.12 kilonewton per meter square. Now, if I want to get the Q net safe, then you have to apply the Q net ultimate by factor of safety. So, this factor of safety value we are taking 2.5 to 3, and if I want to calculate the Q safe ultimate safe or safe ultimate, then Q ultimate divided by the factor of safety. So, here factor of safety is not used because we want the ultimate net ultimate bearing capacity. If it is safe net ultimate bearing capacity, then you have to apply a factor of safety of 2.5 by 3 with this value. That means, 3885.12 divided by the 2.5 or 3, which one you are using. So, next theory is the Meyerhoff's theory, and this is the expression Q ultimate is this one. Here we are using in the Tazdeki's theory, you are using only the shape factor, and here we are using shape factor and depth factor, but inclination factor we are not using, because the loading is acting vertically and at the center. So, it is not inclined, it is not even eccentric. So, it is vertically and the center. If it is not vertically, then you have to incorporate the inclination factor also, but here it is not included. So, these are the factors from the table we are getting, and from there from the Meyerhoff's theory also in Q 64.1 and gamma 93.7 and phi value is equal to 40, corresponding to the phi value 40 degree, and so that is why we are using this value 4830.11 by using the Meyerhoff's theory. And remember, the another thing I want to mention, that here your phi value is greater than 36 degree. So, this will be the local shear failure. So, that means we can use this phi directly as the phi value is greater than 36 degree. If it is less than 29 degree, then you have to, or equal to 29 degree, then you have to go for the so, it is phi is greater than 36 degree. So, we have to go for the general shear failure. So, that is why you are using this equation. So, if your phi is less than equal to 29 degree, then you have to go for the local shear failure. So, but as the phi value is greater than 36 degree. So, remember that. So, when you using this equation, so check that what is the phi value. So, if the phi value is greater than equal to 36 degree, then you have to go for the general shear failure, and all these expressions or theories are developed for general shear failure. So, directly we can use these theories for, because here phi is 40 degree. So, that is why you are using that. Later on I will solve a problem where the phi is less than 29 degree, then you can see how we can solve those problems. So, but for general shear failure, so we have a, so this is the value for the Meyerhoff's theory, and then similar to the Hansen's theory, if I use and we use the NQ and the N gamma by Meyerhoff's chart, NQ and NC same. So, we are using NQ because NC value here this term we are not considering, because that NC value C value is 0. So, first term is vanished. So, NQ is same as the Meyerhoff value, but the N gamma is different. So, that is why we are taking N gamma from the chart corresponding to 40 degree, and if I put all these correct factors and the bearing capacity factors, then we will get the net ultimate bearing capacity is 3328.82 kilonewton per meter square for Hansen's theory. Now, similarly for the Weissig's theory, this NQ is same as Meyerhoff and Hansen, but N gamma is different. So, and we have this factor which is similar to the Hansen's factor, this SC S gamma dq d gamma, and we are getting, if you put this value, we will get these values here 4085.77. Now, as per the IS code is given in this form, this net bearing capacity, ultimate bearing capacity, and these are the factors for IS code, and these NQ and N gamma, they are all same as the Weissig. So, and if I put value, if I put these things into this equation, we will get this value. And remember that in many of the textbook you may find that they are using the net ultimate value in this form. So, that you can use, but I would recommend that you calculate the net ultimate in this way, that first the ultimate minus gamma w, because this is true for the there will be no problem if it is Tarzaki's bearing capacity, because there is no factor like SC, DC, IC is there, but in other cases if you write in this form, then you are also multiplying these factors IC, IQ, DQ and SQ with the gamma df. So, that I will recommend that you use in this form. Okay? Because if you multiply that, there will be a very slight difference, but in because there will be only say 1 or 2 or say 5-10 kPa difference, but okay, I will recommend that you use in this way. Okay. But IS code has already recommended to use in this form. So, that is why we will use this way on in case of IS only, but other case we will use in this form. So, in the IS code also if I put this value, this will give you this value. So, now so these are the summary of the Tarzaki's net ultimate bearing capacity, then Meyer-Rab, then Hensen, then basic, then IS code, and you can see that among this the Meyer-Rab bearing capacity is giving the maximum value, and then the Hensen is giving the lowest, and but these other three Tarzaki, basic and IS code are almost same, almost a similar type, but these two are this is slightly lower and this is slightly higher. So, but depending upon, as I mentioned, so these theories are when compared with the field data, then it is found that for cohesive soil Hensen theory is giving better correlations as compared to the Tarzaki's theory, but Tarzaki's theory we are still using because it is very simple and it is given, you can see this more or less the similar range of data. So, next one, as I mentioned that what will happen if your phi value is less than 29 degree, because in previous case it was greater than 36 degrees. So, it was general shear failure. Now, our phi value is 29 less than 29 degree. So, it will be the local shear failure. Okay. So, local shear failure, so here I am just using one theory. So, similarly you can use it for the other theories also. For the local shear failure, so this is the expression, I am using the Tarzaki's theory. So, this is the expression, instead of NQ I am using NQ dash, and NQ n gamma, instead of n gamma I am using n gamma dash. So, now what we will do, as there is no cohesion value is there. So, that means here we have only phi value. So, and then that is why we can get the phi dash or the phi m, this is phi dash or phi m, and that is tan inverse 0.67 or 2/3 tan phi, original phi. So, if you use this will be the 15 degree. Now, this phi m or the phi dash now we will use as a new phi, and we will calculate the bearing capacity factor from the Tarzaki table corresponding to this new phi. So, that means from the table, if you look at this table, that is corresponding 15 degree, this is NQ is 4.4, N gamma is 2.5. So, here also NQ is 4.4, N gamma is 2.5, this is for the local shear failure. And then other things are same. So, we will get a value is 121.95 kilonewton per meter square. Again this value is meter cube, kilonewton per meter cube. So, this is the, if it is the local shear failure. So, next thing that I will discuss, that this is the, that if the value is in between the local shear failure and the general shear failure. So, what will happen if the value is in between local shear failure and the general shear failure. So, because here you can see the phi value is taken 35 degree, which is less than 36. So, it is in between local shear failure and the general shear failure. So, in this case what we will do, first we will calculate the NQ and the N gamma corresponding to actual phi, that is 35 degree. Then we can get the phi m for the local shear failure, as I discussed in just previous problem, and that phi m we are getting just this phi m . So, this phi m is equal to tan inverse 2/3 of tan phi. So, this is now it is given 25 degree. So, you get the corresponding NQ and N gamma value from the Tarzaki's table, and that is given 12.7 and 9.7. So, now it is in between that. So, now what we will do, suppose we have this is the NQ dash, that is the local shear failure, and this is the value for NQ. So, general shear failure, and this difference of angle is 36 minus 29. Okay? And then you are linearly interpolating that, and it is in. So, this is for 36 and this is for 29. Okay? And here we are here, that is say 35. So, this is the difference of 29, and then what will, so that will be basically the 12 bar means the NQ dash plus the NQ minus NQ dash, then into that your phi value minus 29 degree divided by 36 degree minus 29 degree. So, this is the expression, because we are doing the linear interpolation. So, that way similarly for the N gamma also. So, your NQ bar will be this value. Similarly, we can get for N gamma bar also. So, that is the, that way we can determine the N gamma NQ bar, and then that value we are using here, and we will get a value here 1569.99, that is kilonewton per meter square. So, this is cube. So, this is the value if it is in between local shear failure and the general shear failure. So, before I finish today's lecture, then I will show you one last problem that that we are talking about, that if your phi value, if you look at this problem, it is the same problem we are taking. So, if your phi value is 20 degree, but there is a C equation. So, as I mentioned that if it is a C phi soil, then this phi value only will not indicate that whether it will be a local shear failure or general shear failure. In that case, you have to go for that stress strain curve, and I have already discussed that how you will get this value. So, now here from the stress strain curve, it is mentioned that here the general shear failure will occur. So, if nothing is mentioned in the question, then you will be treated, this will be the general shear failure. If there is a local shear failure, then it will be indicated that there will be a local shear failure if it is a C phi soil. Otherwise, it will be a general shear failure. Here nothing is mentioned, so it will be a general shear failure. So, in the general shear failure, so that is why we will not reduce anything, we will use the same phi value, same C value, and we will get the NC and N gamma for the same phi. And so, that means here we are using 20 degree phi using Tarzaki's table. So, NC N gamma. So, this value we are putting. So, we will get the bearing capacity, that is 1254.45 kilonewton per meter square. And remember that if it is mentioned that there will be a local shear failure, then you have to use the Cm, nu Cm by 2/3 of C if local shear failure, and your phi m will be tan inverse 2/3 of tan 20 here, because your phi value is 20. So, that nu phi you calculate and get the NC N gamma corresponding to that nu phi, and then put the, instead of C you put here we are getting 50. So, it will be 2/3 of 50 and the corresponding NC N gamma and NQ value, and then we will get the bearing capacity. So, in this I am finishing this today's lecture. And so, in the there will be one more problem that I will solve in the next class, that how I can incorporate the water table effect in the bearing capacity equation. So, next class I will first solve that problem, then I will go for the settlement calculation part, which is also very important, because we have two criteria. One is bearing capacity. So, till now I am discussing about the bearing capacity. So, next class first I will solve the water table problem effect, and I will solve the how to incorporate the water table into the bearing capacity, and then I will discuss about the settlement criteria of the foundation design. Thank you.